In our previous lecture, we obtained the state equation for circuits that were linear time invariant. And in this lecture, we will see that the state equation approach is very powerful in the sense that it's also easily applicable to more general situations like nonlinear circuits or linear time varying circuits. To see how that's possible, or at least to get some idea, because that's quite a deep subject, let's consider some simple examples. Okay. Our first example is a circuit that contains linear time varying elements. Okay. Time varying elements. Okay. For linear time varying or nonlinear dynamic elements, meaning capacitors or inductors, it turns out that it's easier to work with instead of voltage and current, capacitor voltage and inductor current, as we usually do for the LTI case, to work with the charge for the capacitor instead of the voltage and flux for the inductor instead of the current. Okay. For instance, for a linear time varying or nonlinear capacitor, it is easier to work with charge instead of the regular voltage, which we do for linear time varying systems. Instead of voltage. As state variable. Okay. And the dual statement is also valid, meaning that for linear time varying or nonlinear inductor, okay, it is easier to work with flux instead of the inductor current. Okay. Now we're gonna apply this way of looking at things in our linear time varying circuit example. Okay, now the circuit that we are to obtain the state equation is given here. We have three dynamic components, two inductors and one capacitor. The input is single here, just the voltage of the independent voltage source. We have here an LTV, linear time varying resistor, where the resistance is a function of time. And we have L1 of t for our first inductor, whose current is I1, and we have L2 of t for our second inductor, inductance of the second inductor, which is also time varying, L2 of t, and this is the current of the second inductor. We have time varying capacitor, because the capacitance is a function of time. This is our capacitor voltage, Vc, and here we have the time varying linear resistor, R2T. Furthermore, those two inductors happen to be coupled. Okay, so here we have the dots, and the the mutual inductance is also time-varying and represented by M of t. And for this circuit, we will try to obtain the state equation. Okay, x equals ax plus b vs. Now, since the elements are time-varying, our A and B matrices are expected to be functions of time, as opposed to constant matrices for the LTI case. Okay. Now, what we have is, okay, let's write down the terminal equations. We have, okay, we have phi1, phi2, so this is the flux associated to the first coil, and phi2 is associated, the flux associated to the second coil. And what we have is the vector of fluxes equals inductance matrix times the vector of currents, I2. And the entrances, okay, the entries of the inductance matrix are L1, T, L2, T, and T, and T. Okay, so that's the flux current relationship of our coupled inductors. And furthermore, we have the parallelized law, rate of change of flux equals voltage. Okay, Y2 dot equals V2. As for the capacitor, the charge, let's call it Q of C, equals or proportional to, at any given time, the voltage, but the proportionality is not described through a constant, but the time-varying scalar. That time-varying scalar is the time-varying capacitance of our capacitor. And as for the current, what we do is we use the definition of current, which is rate of change of charge. Okay, so those are the terminal equations representing our dynamic components. Now let's pick a state variable, and then once we have, the state vector, and then once we have our state vector, we will try to obtain the state equation. So this is our circuit. For that, let's quickly obtain a graph representation. Okay, so we have here a node, here another node, here another node, here another node, so that makes 4. And finally, this is our 5th node. Okay, 4, and this is our 5th node. Okay, so this edge represents R1, this branch represents L2, this branch represents the capacitor, and then we have this branch representing R2, this branch representing Vs, and also we have this branch representing the first coil. Let's give some directions. Now let's pick a tree, a proper tree, which should exclude as many inductors as possible. And it turns out that there is only one such choice, and it's this. Okay. It also satisfies the other constraints, like it contains the voltage source, and also it contains all the capacitors. Okay, or as many capacitors as possible. In this case, we just have one. So this is our tree. Okay. So if we go with the usual procedure to choose a state, what we have to do is choose the capacitor voltage. okay, because that belongs to our tree, and also choose inductor currents because they belong to our core tree. But since this is a time varying circuit, it's easier to work with. Instead of currents, with fluxes for the inductor, and instead of voltage, with charge for the capacitor. Therefore, let our state vector be x equals flux 1, flux 2, these two coming from the inductors, and finally we have, instead of Vc, Qc, the charge of the capacitor. And now what we want to do is exactly what we wanted to do for the LTI case, that is obtain phi1 dot, phi2 dot, and Qc dot, okay, in terms of our formulation variables phi1, phi2, Qc, and also possibly the input Vs. Okay, so for that, let LT, this is our inductance matrix, which is time varying for this circuit. Suppose that it's invertible, it's non-singular, and its inverse is represented by gammas, gamma 1, 1, t, gamma 1, 2, t, gamma 2, 1, t, but we take an inverse of a symmetric matrix, therefore the inverse should also be symmetric, meaning that we can make use the same notation for the off-diagonal terms, gamma 1, 2, t, and here we have gamma 2, 2, t. Okay, so this is our inverse of the inductance matrix. And then using that inverse, we can write currents, okay, in terms of fluxes. I1, I2 equals gamma 1, 1, t, gamma 1, 2, t, gamma 1, 2, t, gamma 2, 2, t, multiplying the flux vector. Okay, now we're ready to obtain the state equation. For that, let's start from our first state variable, namely phi1. The question that we want to answer at this point is what's phi1 dot, because that's what we need for the state equation. So let's try to figure out phi1 dot. What's phi1 dot? Phi1 dot, okay, by Faraday's law equals the potential difference across the terminals of the first coil, okay, plus minus V1. And then let's try to express this voltage V1 in terms of our state variables phi1, phi2, Qc, and also perhaps the input Vs. For that, what we're going to do, we're going to make use of KVL. Okay, this is V1 we're talking about. So let's write KVL in the fundamental loop defined by this quaternion branch. That means this voltage minus that plus this voltage plus minus, and plus this voltage plus minus must equal 0. In other words, V1 equals minus VR1 plus Vs. Okay, this is Vs, this is VR1. Now Vs is good because it's our input, it's one of our formulation variables. How about VR1? VR1 is R1 times, okay, the current passing through it, this direction of VR1, and the current passing through R1 in that direction is simply I1 plus I2, okay, from KCL written on that node. So we have R1 times I1 plus I2. Well, we should keep in mind that this R1 is R1 of T plus Yes, and finally, we can express those two currents, I1 and I2, in terms of our state variables using this inverse matrix. Okay. So therefore, that equals minus R1 times gamma 1, 1 plus gamma 1, 2 times phi1 plus gamma 1, 2 plus gamma 2, 2 phi 2. Okay, this whole thing is I1 plus I2, which we'll obtain from this matrix equation. And what else? Plus Vs. Okay, so let's call this equation 1. So what we have obtained, therefore, is phi1 dot equals V1, V1 equals that equals this. And this equation is in nice form because it's only in terms of our formulation value. Okay, so let's do the same thing for phi2 dot. Phi2 dot equals what? Okay, so what we have is phi2 dot equals V2 by Farabay's law, and V2 equals what? Writing again the KVL equation on the fundamental loop defined by this coil-free branch. Okay. Correspond to second coil of our coupled inductors. We would have that the sum of all these voltages that appear on the outer mesh must sum to 0. And what's all those voltages? Okay, if you write that equation and then pull V2, okay, to the left hand side, what you obtain is the following: minus Vc minus R2 phi2 minus VR1, which is R1 times I1 plus I2, and finally plus Vs. Okay, so this is VR2, this is VR1, Vc, Vs. So basically, what we did is we wrote KVL on the outer mesh for the fundamental loop, and then from that KVL equation, we obtained V2, the voltage of the second coil. So this is therefore phi2 dot. The problem with that is that it contains certain variables that are not our formulation variables, like Vc. We have to express this in terms of the charge, and we have I1 and I2. We have to express those in terms of fluxes, but that's easy to do. Let's do that. So that equals Vc. Minus Vc. Vc is Qc over time varying capacitance C. Okay. Minus R2 times I2, and I2 is from our inverse inductance matrix expression. Right. Gamma 1, 2, phi 1 plus gamma 2, 2, phi 2. And we have minus R1 times I1 plus R2, which is here. Gamma 1, 1 plus gamma 1, 2, phi 1 plus gamma 1, 2 plus gamma 2, 2, phi 2, and finally plus Vs. Okay. Now, that's what phi2 dot equals to, and this equation in nice form because everything is in terms of our formulation values. So there's only one thing left, and that's the dot for the last state variable, which is the capacitor charge. Let's quickly figure that out also. What's QC dot? QC dot by definition is the current passing through the capacitor. Okay, IC. And IC equals This is IC because that's the polarity of the capacitor voltage. Therefore, IC equals I2. It's the same current. And I2 equals, in terms of the fluxes, gamma 1, 2, phi 1 plus gamma 2, 2, phi 2. Okay. Now we can enter this IC, and that's our QC dot, which is only in terms of our state variables. Okay, so we already called this equation 1. Let's call this equation 2, right to that equation, and finally, let's call this last equation 3. All that remains is to put these equations in matrix form. Let's do that. So 1 and 2 and 3 implies x dot equals, will be a little bit messy matrix because we have lots of things to take care of. X plus B matrix times our own input, which is Bs, okay, make our state equation. Okay. So the first state variable is phi 1. So for the first row, therefore we have to look at the phi 1 dot equation, which I just erased. It was here. So what we have is minus R1 gamma 1 1 plus gamma 1 2 times phi 1 minus R1 gamma 1 2 plus gamma 2 2 times phi 2 plus 0. Okay, I have to make this a little bit larger. Okay, plus 0 times QC and plus 1 times Vs. That's coming from our first state equation. And then here, then comes phi 2 dot, which is here. Okay, so phi 2 dot equals minus R2 gamma 1 2 minus R1 gamma 1 1 plus gamma 1 2 times phi 1. Okay, we have phi 1 term here, we have another phi 1 term here. So we collect those two terms, and what we have is R2 gamma 1 2 and R1 times this sum. That's our second row, first column entry of our A matrix. For the phi 2 term, we have R2 minus R2 gamma 2 2 and this times minus R1, so that makes a little bit long expression, minus R2 gamma 2 2 minus R1 gamma 1 2 plus gamma 2 2 phi 2. Okay, so I have to carry this a little bit to the right. Minus R1 gamma 2. And finally, for the third state, and we have minus 1 over C QC. That's what this entry should be, minus 1 over C. As for Bs, we have 1 okay over there and put 1. And finally, for the last row, we will get the last equation, QC dot equation. It's quite cleaner compared to the previous two. So what we have is gamma 1 2 times phi 1, gamma 2 2 times phi 2 plus 0 times QC plus 0 times Vs. Okay. So in general, for a linear time varying circuit, LTV state equation reads x dot equals ATX plus BT W. Okay. For the LTI case, we have constant A and B matrices, but for the LTV case, not surprisingly, these entries of those matrices are also binary. Okay. Now, in our next example, we're going to consider a time invariant, but this time nonlinear circuit, and see that we can apply state equation approach to such cases too. This time we have nonlinear circuit, okay, which by definition is a circuit that contains at least one nonlinear component. Okay, so this is the circuit. Ohm, 1 Henry, 2 Farad. Okay, this is IL. This is labeled as V2. So these are linear LTI components: an LTI resistor, an LTI inductor, and an LTI capacitor. But the remaining two components are nonlinear. Here we have a nonlinear capacitor whose voltage is labeled V1. And here we have plus minus V3, I3. We have a nonlinear resistor here. Okay. So we need the terminal equations for those two components, and they're given as follows: I3 equals tangent hyperbolic V3. Okay. So the dependence of the current voltage or voltage to current is nonlinear. This is a nonlinear resistor. And then we have here the nonlinear capacitor. Okay. Now the LTI capacitor is such that its voltage is related to its charge through a line passing through the origin, and the slope of that line defines the capacitance. Okay. Now, the relation between the voltage and the charge for a nonlinear capacitor is not expressed by a line, but through a more general curve to, let's say, Q1 plus Q1 cube. Okay. So the charge and voltage relationship is nonlinear. So therefore, this describes a nonlinear capacitor. Now for this circuit, let's obtain the state equation formulation. So let the state be, okay, suppose that we perform that proper tree selection and so on, and in the end we figure out that all the capacitors and all the inductors must be represented directly in the state. So regularly what we do is we pick, for an LTI circuit, we pick V1, V2 and IL as our state variables, but this time it's okay to choose IL and V2 as state variables, but for the nonlinear capacitor it's easier to choose the charge instead of the voltage. Okay, therefore let our state be Q1. Okay, the charge of the first capacitor, then V2, and finally we have inductor current. So we're talking about a third order system. No, the system doesn't have any independent sources, so that means you don't have any input in the circuit. For a resistive circuit, when you don't have an input, you don't have to really formulate the circuit. You don't have to solve the circuit, everything is zero, okay, automatically. But for a dynamic circuit, for a dynamic system, even if you have no external inputs in the circuit, still you will have some non-zero response, and that's the response due to initial stored energies or initial conditions of the dynamic components. Okay? So even if you don't have an input, it's still an important problem to formulate the circuit. Okay, so having chosen the state, to obtain the state equation, what we have to do is we have to figure out X dot. That means we have to figure out Q1 dot, V2 dot, IL dot in terms of our formulation variables. Okay, so let's do that. Start with Q1 dot. Okay, so what's Q1 dot? Q1 dot, by definition, equals the current passing through the capacitor. Okay, so we're talking about this current. Now that current, okay, by writing KCL in this node equals minus I3 minus IL. Okay, so this current equals minus this current minus plus minus that current plus minus that current. Okay, so we're talking about I3, IL, and the negative of this current. Okay, so we already have written I3 and IL, and finally we have this current, which is simply the voltage drop across the resistor divided by 2, which is V1 minus V2 over 2. V1 minus V2 over 2. Now, we're not done yet for Q1 dot because we have to somehow express I3 and V1 in terms of our formulation variable. So let's do that. So that equals minus tangent hyperbolic V3, okay? And V3 is no other than V1, so we can write, instead of this term, minus 10H V1 minus IL minus V1 minus V2 over 2. Okay, we have got rid of I3, but still we have to take care of V1, and for that we will use the terminal equation for our nonlinear capacitor. So if you do that, let's see what you obtain. Minus 10H V1. V1 is 2Q1 plus 2Q1 Q minus IL minus V1 over 2, which is Q1 plus Q1 Q, and finally plus 1/2 V2. Now everything is fine. Everything is in terms of formulation variables. Move on to V2 dot. Okay. What's V2 dot? V2 dot is 1 over C2 times I2. That's the terminal equation for the capacitor, second capacitor, which is LTI. And what's I2? I2 equals, we're talking about this current, again writing KCL at this node, we can see that I2 equals IL plus the resistor voltage divided by the resistance, and that equals IL plus 1/2 V1. V1 is here. Q1 plus Q1 cube and minus 1/2 V2. Okay, so that's V2 dot. And finally, we have IL dot. IL dot. IL dot equals, by term equation, 1 over L times the voltage. L is 1, therefore V equals VL. Okay. And VL is V1 minus V2, and V1 is Q1, 2Q1 plus Q1 cube. Okay. So we're done with expressing the time derivatives of our state variables in terms of our state variables. Okay. Now all that remains is to put those three equations into a single equation, which will be a nonlinear vector equation. Okay, so finally we have Q1 V2 IL. This is our X. Now X dot equals some vector, okay, which is a function of the state. So the first entry of that vector is minus tangent hyperbolic 2Q1 plus 2Q1 cube minus Q1 plus Q1 cube plus 1/2 V2 minus IL. Okay. Basically, we just copied this right hand side in the first equation. Then V2 dot equals this expression here. So we have therefore, right, Q1 plus Q1 cube right. So, excuse me. So this is V2 dot is 1/2 I2. This here we have is I2. Therefore, in order to write V2 dot, we have to divide this thing to 2. Okay. So here we have therefore 1/2 term. Okay. 1/2 Q1 plus Q1 cube minus 1/4 V2 and plus 1/2 IL. Okay. And for IL dot, we have 2Q1 plus Q1 cube minus V2. Okay. And that's our nonlinear state equation. So in general, a nonlinear state equation reads X dot equals f of X and W. X is our state vector and W is our input vector. In our case, we didn't have any W because we didn't have any inputs. Okay, so let's also write that down. In our case, we didn't have any input. Therefore, have a slightly simpler expression. Okay, x that equals f of x only, where f is a function, okay, or a mapping that takes vectors from R3 and maps them to other vectors in R3.